Hey, Physics 30s, how's it going? So we're going to continue our lessons here. We're going to talk about reflection today. So we're going to start off nice and easy, and then we're going to talk about curved mirrors, specifically concave and convex mirrors. So what we know about the law of reflection, you probably learned this in Physics 20 as well, is if I'm just going to scroll down to this next page here, is it's pretty easy. So we have a surface. Let's say we have a nice little surface. We have a point of incidence. That's where the incident ray is hitting. Now, this is a wave front, an incident waves. You have to remember that these waves they're going like this, right? They're transverse waves. So usually we don't drop, but these are just going to be, these are the crests of a wave, and they're traveling this way. And then these are the crests of the wave, and they travel back. So they're going to hit this surface. They're going to reflect off this point. We only draw just the ray part of this. So you hit the surface at a very specific angle. So this angle is theta. We call that theta incidence. So the incident ray hits the surface at the incidence, and then it reflects back at the reflected angle. And what we know about the law of reflection is that the incident angle and the reflected angle are the same thing, right? That's just a simple one. Now, is very key about how you measure or where you measure the angle from. So the angle that we see here is measured to the normal line. I'm just going to see if I can get that cursor out of the way. And the normal line is always perpendicular to the surface that it hits, right? So that's very key, that you're measuring to this normal line, the line that is perpendicular to the surface that it hits. Now, the thing is that usually the surface is not flat. Like, yeah, sure, you got flat mirrors. I don't have one around here. You got nice smooth mirrors. But what if the surface is not smooth, such as this piece of paper, right? The reason it's not reflective the way glass is just because of how the divots in here reflect the light in different directions. So you don't get a perfect reflection off it. So we have these two types of reflection. We call that specular, and then we also call it diffuse reflection. But they still follow the law of reflection. Now, specular reflection is the smooth reflection. So you got this surface right here, nice smooth surface. The incident ray hits it. Now the surface is nice and flat, so the normal line goes straight up. So this is my normal line again. Okay, and then the ray is going to bounce off this direction. Now the reason this is called specular is because if all the rays come in parallel to each other, all these incident rays, here's another incident ray, here's another incident ray. If all these incident rays, they're all going to bounce back at the same angle because the normal lines are all parallel to each other. There's a normal line there, there's a normal line here, and there's a normal line. All of these normal lines are parallel. So you get what we call specular reflection. They go in the same angle, they come out the same angle. They all look the same. Now, diffuse or irregular reflection is when the surface is bumpy or rigid, and when the rays come in, this is the surface down here. Again, I'm doubting the choice of my rainbow color here. It's going to come in, it's going to hit the surface. It's going to hit the surface with different normal lines. So if I were to try to draw the normal lines here, I don't know how thick this marker is. Let's see. Too thick. Okay. If I were to try to draw the normal line on this surface, I'd look at the, first of all, what's the tangent, and then draw the normal line. So there's the normal line for that one. This one here, that looks like the tangent there. My normal line is going this way. You notice that normal line is not parallel to the previous one. This one here, when it hits this surface, my normal line is going to go up this direction. And this one here, my normal line is going off that direction. So I got all these different normal lines, and then when they bounce off, they're going to bounce off wildly in different directions. So all these reflected rays, and this one's even going that direction for some reason, and this one's going up this way. So I got all these rays going off different directions, so you don't get this nice reflection. You get like seeing a mountain in a wavy lake. In a nice smooth lake, it looks really good when there's no wind, but as soon as there's wind, you're going to get this kind of weird ripply pattern. You may not even see the mountain all together properly. Now, for most of what we're going to do, the majority of what we're going to do is we're going to do regular specular reflection, or semi-regular, where the surface is smooth but it's kind of curved instead. Okay. Okay. So now when you look into a mirror, say you're just looking into just a plain mirror, okay, what you see is, say, an image on the other side. You see something behind the mirror. Right? You know physically that doesn't exist, it's just an image, but it looks like it's behind the mirror. You see something there because your eye is being tricked into thinking there's something there, because your eye and your brain understands that light should travel in a straight line. It shouldn't curve around things. So if it thinks it's traveling in a straight line, your eye is going to perceive it to be where that ray is coming from, where this beam of light is coming from. If you ever do any computer programming or any three-dimensional computer programming, you're going to be talking about ray diagrams or rays. That's actually a new thing. It's a ray reflection, where previously, back in the day, they used to think how you saw things is that your eye shot things out of your eye, it hit something, and they came back. Now what we know is that light is kind of bouncing out from all sorts of things. It hits an object, so it hits my microphone, bounces off my microphone, and it comes towards my eye. So when we draw ray diagrams, we usually think about, okay, here's an object. This is the object on the same side as the observer. So you're over here. You could draw your face over here, looking pretty happy, right? So you're looking at this mirror. There's an object over here by your chin, okay? You can't really see the object past your nose here or past your chin, but you can still see the object, the image of the object behind the mirror. How that works is that rays bounce off the object in all different directions, just like the law of reflection here. You've got all these incident rays hit this point of incidence here and then reflects off, and they're going to reflect off in all different directions, right? In all different directions. And then some of those rays are going to follow the right path, hit a point of incidence here, reflect off the surface, and then into your eye. So one of these rays will be this one here, and then into your eye. And you can see that there's a few of them that might do that because your eye has some thickness to it. So your eye is going to release, or going to take in more light, right? But your eye doesn't perceive the bending. Your mind doesn't perceive that it's reflected off somewhere. So what it does, it traces those lines back until they converge at a single point back here, because that's where they came from. They came from a single point down here. They came all from this little point down here, going in all different directions, but they came from a point, and they spread outwards. So your mind is perceiving that all these beams are actually coming from this object, converging out from this one, or diverging out from this one, sorry. So these beams are traced backwards to this dotted line behind the mirror, and your mind perceives an object back here. So we call this the image, obviously, right? There's nothing really there, but your eye perceives that something should be behind the mirror because that's where it thinks the light is coming from. It's coming out from that point. So if I trace it back, that's where it should be. What's it called? Ray tracing. Sorry, that's what it is. So you ray trace it. So you're tracing back, trying to figure out where this came from. So it thinks it comes from behind this mirror. Now, there's going to be a few things we're going to be talking about, the properties of images. Now, the two main properties that we have here is if the image is formed behind the mirror on the opposite side of the observer. So here's the observer down here, the observer, right? If it's on the opposite side of the observer, I'm just going to write that in there. If it's on the opposite side, we call that a virtual image. Most things you see are virtual images, right? Can't really see it. I can give you these mirrors here. Here's a mirror, okay? So that there is a virtual image, okay? Nicely circle the mirror can fit nice perfectly in that little circle there. you're perceiving this to be behind this mirror, but obviously it's not behind the mirror. So this is the virtual image. It's hard to see a non-virtual image. Those are usually produced using mirrors like this, right? This is a concave mirror. The other one is a convex mirror. So you can see that there's an inside this one here. So this would produce this is now a virtual image. Apparently, this somewhere right about here is considered a real image in there. You can't see it based on how clean this mirror is. It's really hard to see it unless you have a three-dimensional panel. Okay. But if it's behind the mirror, if the image is formed behind the mirror, then you have a virtual image. If the image is formed in front of the mirror, then we have what we call a real image. And we're going to see this real image in action during the lab. Now, what I mean by action is that if you think about a projector screen, there's a projector screen. We're on the same side as the observer here. When we see an image on this screen, that is considered a real image because the actual device up there that's producing the image, that's producing the original image before it goes through all the lenses and stuff, is on the opposite side as the observer. And this would be on the same side as the observer. So this is technically considered a real image. Okay, so we got virtual images, you got real images. We also have other characteristics as well. When we talk about these, we talk about, sometimes we talk about the magnification. And some of these are called qualitative and some of them are quantitative and some of them actually have two versions. Remember, qualitative is more of a description and quantitative is more of a number. So magnification actually has two pieces to it. It has qualitative, where you could say that this is the wording that we're going to use. You can say this is enlarged or diminished. Okay, diminished. And yeah, you'll see this wording as well in scientific journals and other future physics classes. They'll say enlarged and diminished. They won't say it's bigger or smaller. They're just using these words to differentiate between other times you might use bigger and smaller. But this could also be a magnification number. It could be a number. So it could be qualitative. You could say it's 2 times enlarged, or it's half the size it was before. So you could say that's diminished. So it's actually physically a number. It's a multiplication number. So it's either one of those, either one of these two descriptive words, enlarged or diminished, or an actual number. Now, attitude. Attitude is the direction of the image itself. Is it the correct way or is it upside down? Now, out of my 2 mirrors here, I'm going to bring these mirrors back down. Like this attitude is the same way. You can see the desk is in the same direction. The floor is up down there. You can see the roof is up here. So this attitude, the one you see here, is what we call erect. It's the same orientation. The image is the same orientation as the objects that it's reflecting. So that attitude is what we call erect. If it's inverted, it's upside down. So I bring this back here, you can see that this is upside down. You can see that here's with the roof, there's the floor in my image. This is an upside down inverted image. It's kind of hard to see, but if I point upwards, you can see the roof there. That would be the ground. Now, yeah, so it's they're on the wrong, everything's upside down here. I put my hand there, I can't really reach that far, but it is upside down. So that would be an inverted image. So erect or inverted. Now, there's no number for that. There's just a qualitative descriptive word. That's all that is. Position is how far the distance from the mirror. Now, think of this sometimes. The distance the object is from the mirror, so how far away, say, the camera is to this mirror, and then you have to think, sometimes we talk about the distance the image is from the mirror too. So this is the surface of the mirror. The image is actually behind the mirror. It has a certain distance, a virtual distance, because it is behind the mirror, but there is a distance there. We can actually calculate virtually what that distance would be. Okay. Let's put that back up there. So you can measure that distance, the distance from the mirror, and you have a type. There's two types we just talked about already. We have virtual images or we have real images. So either one of those two. If it's behind the mirror on the opposite side of the observer, or is it on the same side as the observer? That would be a real one. Okay. Those are already kind of described up here. Now, if I go back to the plane mirror has very specific characteristics. This is a plane mirror because it's just a flat mirror. So we're going to be talking about concave and convex mirrors, these kind of curved mirrors. But for a plane mirror, it has some very specific characteristics. So we could say that here, the magnification of this is equal to 1. This is for a plane mirror. Okay. Not like plane as plane and tall and stuff, it's just plane as in a X and Y coordinate kind of plane. So that's why it's spelled this way. So the magnification is 1, is neither enlarged or diminished. It's about the same size. So that's when you're looking into a mirror, thinking, that should be generally what my size is when I'm looking in the mirror. When you're looking into a mirror, the image type is virtual because it is perceived to be behind the mirror. So this is virtual, it's on the other side. It is also erect because your top of your head is where the top of the head should be. Your bottom of your chin is on the bottom. Your left side is on the left side and your right side is on the right side. Right? Technically, your image is not flipped over. It's not flipped in the mirror. It's exactly the way the proper orientation. Your left ear is on the left side. Your right ear is on the right side, right? Your top of your head is on the top. Your chin is on the bottom. So nothing is actually flipped. Your image is not, even though the words look flipped here, it's actually technically not flipped. The words, what's on the left side stays on the left side. Just it looks like it's flipped, even though it's not. Erect, not diminished, virtual, and then my last one. Sometimes I can't remember these as well. Position. It's the same distance. So the image, I'm just going to say here, the image is the same distance from the mirror as the object. Just on the other side. So if I were to measure here the distance from here down and the distance from here down, this would be called distance to the object. This would be called the distance to the image. Those two things, the DI is equal to DO. Okay. Now one's going to be negative, one's going to be positive based on some sign conventions that we use later on, but they're essentially the same. Now the height for the magnification, you can also think of the height of the object divided by the height of the image ends up being 1. So the object is no bigger than the object of the height, or the object and the image are both about the same. Okay, I'm going to finish off this video here. The second part, we're going to be talking about curved mirrors and how to reproduce images using curved mirrors. And we saw some examples from my mirrors up there. I'll see you in the next video. Bye.